Example 5, graphing a family of functions. How does the graph of f of x equals 1 over x squared plus 2x plus c vary as c varies? So let's go ahead and graph them. Okay, so if we take a look at graph 1 and graph 2, these are special cases of where c is equal to 2 and c is equal to negative 2. So let's go ahead and identify those. Okay, so when c is equal to 2, you can see down here, here's where c is equal to positive 2. And here's where c is equal to negative 2 for that function. Okay, and what we want to do is we want to be able to show two different looking curves. So before drawing any more graphs, let's see what the members of this family have in common. So if you take a look at these two graphs, okay, this one looks a little bit different than this one depending on the value of c. So let's find the limit of this function as it approaches positive and negative infinity. So if we wanted to find the limit of this function, so the limit as x is approaching plus or minus infinity of 1 over x squared plus 2x plus c, well, that's going to give us a value of 0. Now that is for any value of c. Okay, they all have the x-axis as a horizontal asymptote if you look here. So here we have y is equal to 0, y is equal to 0 as the horizontal asymptote. So let's go ahead and define that. So we can see here that for any value of c, they all have the x-axis as a horizontal asymptote. So a vertical asymptote will occur when a denominator, x squared plus 2x plus c equals 0. Now, if we wanted to solve this quadratic equation, then we would get the following for x. X is then would equal negative 1 plus or minus the square root of 1 minus c. Okay, now we need to look at the scenario of when c is greater than 1. Well, if we look here at c is greater than 1, when c is equal to 2, we can see that there isn't a vertical asymptote. So when c is greater than 1, as in graph 1, we have no vertical asymptote. Now when c is equal to 1, the graph is going to have a single vertical asymptote at the following. It's going to be x is equal to 1. Okay, and we'll figure out why but let's take a look at the graph first. Okay, this is the graph where, and we'll just call this number 3, where if this is f of x, which is equal to 1 over, and this is x squared plus 2x, this is 1 now, and this is where c is equal to 1. Okay, we can see that we get this vertical asymptote at x is equal to 1. And the reason being is because if we want to find the limit, not 1, I'm sorry, it's negative 1. If we want to find the limit as x approaches negative 1 of that function where we have 1 over x squared plus 2x plus 1. Okay, so what does this equal? So if we factor this denominator as x approaches negative 1, well, this is the limit as x approaches negative 1 of x plus 1 squared. So therefore, that's going to be 1 over 0, which is going to give us infinity. So that proves the fact that we have a vertical asymptote at negative 1. Okay, now, if we let, when c is less than 1, okay, there are two vertical asymptotes. So we can see here that there's two vertical asymptotes in this graph where it's less than 1. Okay, so if we wanted to find that vertical asymptote using the quadratic formula, we would have x, which is equal to negative 1 plus or minus the square root of 1 minus c. Okay, and so now what we want to do is we want to be able to compute this derivative. Okay, so if we want to compute the derivative of this function, Okay, so let's go ahead and write out the original function. So we know that the original function is the following. So we know that f of x, which is equal to 1 over x squared plus 2x plus c. If we want to find the derivative of this function, well, in the numerator we have the derivative of the denominator, which is going to be 2x plus 2 divided by the denominator is going to be squared, so x squared plus 2x plus c squared. Okay, now if we wanted to find the derivative of looking at the first function up here, so let's go ahead and find the derivative of this function. Okay, so find the derivative of this function is going to be 2x plus 2 over x squared plus 2x plus 2 squared. Okay, so I want you to look at the graph here, because this graph here represents the derivative of 2x plus 2 over x squared plus 2x plus 2 squared. But in general, we're going to look at this derivative here. So this graph shows that f of x is equal to 0 when x is equal to negative 1. So we can see that right here. So that tells us that f of x is equal to 0 when x is equal to negative 1, which is right there. Okay, now we know that the derivative is going to be greater than 0 when x is less than 1. And that should be less than negative 1. Okay, so we can see here that this derivative, okay, is going to be here, which is greater than 0, when we can see here when it's less than negative 1. Okay, and then we also know that the derivative is going to be less than 0 when it's greater than negative 1. So we can see here it's going to be below the x-axis. And so therefore here it's going to be greater than negative 1. Okay, now for when c is greater than or equal to 1, this means that f is going to be increasing from negative infinity to negative 1, and it's decreasing on negative 1 to infinity. Now for c being greater than 1, there's going to be an absolute maximum value of f of negative 1 equals 1 over c minus 1. For c less than 1, we have f of negative 1, which equal to 1 over c minus 1 is a local maximum value, and the intervals of increase and decrease are interrupted at the vertical asymptotes. So now, if we take a look a little further, okay, the figure below is a slideshow displaying the 5 members of the family, all graphed in the viewing rectangle between negative 5, 4 and negative 2, 2. So as predicted, okay, if we look at c is equal to negative 1, okay, the value, this is the value at which the transition takes place from 2 vertical asymptotes to 1 and then to none. And so as we see that c increases from 1, which goes to 2 and then 3, we see that the maximum point becomes lower. And this is explained by the fact that 1 over c minus 1 approaches 0 as c approaches infinity. So now as c decreases from 1 going to c is equal to 0 and c is equal to negative 1, the vertical asymptotes become more widely separated because the distance between them is 2 times the square root of 1 minus c, which becomes large as c approaches negative infinity. So again, the maximum point approaches the x-axis because 1 over c minus 1 approaches 0 as c approaches negative infinity. So there is clearly no inflection point when c is less than or equal to 1. Okay, but for when c is greater than 1, we can calculate the second derivative. And so that second derivative is going to be the following. The second derivative of x is going to equal 2 times 3x squared plus 6x plus 4 minus c divided by x squared plus 2x plus c to the third power. And we would deduce that the inflection points would occur at the following using the quadratic formula for the bottom here. So therefore, it would be -1 plus or minus the square root of 3 times c minus 1 divided by 3. And so the inflection points become more spread out as c increases, and this seems plausible from the last two parts of the figure above.